Hello everyone. Thank you for joining us. In today's webinar, we will be covering principal advantages and applications of induction heating. In addition, using EMS for SOLIDWORKS software, we will address various design and simulation challenges of an induction hardening application. Before discussing today's agenda, let me introduce us. My name is Cal and I handle sales and marketing division of our company. My colleague Asma is a senior application engineer and an expert user of EMS software. She has an extensive knowledge in the field of low-frequency electromagnetics and will be delivering the technical part of today's webinar. Before moving on, I would like to highlight few points. Please use the chat window to send in your questions and we'll try to answer them at the end of this presentation. A webinar recording link will be sent to all the registrants via email in few days. Our agenda for today is following. I will briefly talk about our company EMWorks, where we are located and what products we offer. Then my colleague Asma will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its software users. Now let us take a quick overview on our company EMWorks. We offer 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. Our products are gold certified by Dassault Systems SolidWorks Corporation since the year 2008. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany in Europe region. Let us talk a little bit about our company products. We offer 4 products with various add-ons covering a wide frequency range. Our first product is called EMS, which is used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, cables, bus bars, induction heating, permanent magnets, actuators, circuit breakers, transformers, and electrical machines. Our second product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers many applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is called EMWorks 2D, which currently offers static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition is Motor Wizard software, which is a template-based motor design product. It offers analytical and finite element analysis of brushless DC motors. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, we will be using EMS for SolidWorks product to design and simulate an induction heating application problem. Let us briefly touch upon the licensing structure offered by EMWorks. We offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the 2 programs, our licensing structure is usually annual based. The topic for today's presentation is simulation of induction hardening using EMS for SOLIDWORKS. My colleague Asma will focus on various topics including working principle of an induction heating process, advantages and applications of induction heating, and design and simulation challenges of an induction hardening application problem. I would now request my colleague Asma to take over and present the next part of this presentation. Thank you.
Thank you, Carl. Hello, dear attendees. First of all, I want to thank you all for joining us today. I am Asma, Senior Application Engineer at EMWorks, and today I'm going to represent you the technical part of today's webinar about simulation of induction hardening using EMS for SolidWorks. First of all, let's have a look at our agenda for today. We will start with a quick overview about induction heating, the main principle, advantages, and applications. Then, we will move to a well-specified application of induction heating, which is the induction hardening process for material heat treatment, in which we are going to discuss the main design and simulation challenges of this process, and we will cover the main EMS capabilities that will be used for such heating process. Then we will move to a live demonstration of EMS interface inside SolidWorks. Later on, and using simulation, a detailed analysis of induction hardening process of a sphere gear will be done. We will study the impact of some processing factors on the gear temperature, and we will try to estimate the generated electromagnetic and thermal stresses. And finally, a conclusion. As you know, induction heating is one of the most clean, efficient, and precise contactless tools for material heating, and it is particularly useful where highly repetitive operations of heating are performed, especially for industrial processing. Now let's go through a brief memory refresh about the basics of this phenomenon. Simply stated, when applying an alternating current inside the coil, a time-varying magnetic field is generated. Now, when exposing a conductor material to this alternating field, an induced eddy currents are created inside it, resulting then high resist flushes, which will heat up the material according to the Joule law. When using high frequency, AC current tends to avoid traveling through the center of the solid conductor, which is called the skin effect. It is then circulating in a thin layer toward the surface of the heated workpiece. In turn, it leads to an increased resistance of the conductor, ultimately resulting in a greatly increased surface heat. The skin penetration depth could be defined by the following expression, including the frequency and the material conductivity property. This process is based on two tightly coupled phenomena, the electromagnetic and heat transfer with their fundamental Maxwell and Ohm's equations. The main advantages of induction heating. It is an energy-saving heating process, controllable by many factors like the heating time, the current supply, the used frequency, and the material to be heated. It allows a rapid and precise localized heating, and it is essentially used for highly repetitive heating, which make it easily integrated into production lines due to its efficiency as a fast, clean, and secure technology. Now let's have a look at some of the main induction heating applications. For the industrial domain, induction heating is essential for heat processing, where highly repetitive operations of heating are performed, especially for material heat processing, like for hardening and tempering, melting, casting, brazing, and even preheating for welding. It is also used for non-destructive testing operations by thermography for crack detection or to heat up the thermoforming molds. For domestic domain, we have the famous induction heating cookers and boilers. Now for medical and healthcare domain, induction heating is essential for hardening surgical blades and also brazing steel for auto-denting parts. In the right, as you can see, some of the application of induction heating which we're investigating using EMS for SolidWorks. We have the induction heating molds, the non-destructive testing for crack detection by thermography. We have the induction heating cooker, the preheating for turbine blades, and also for hardening steel tubes, etc. For today's webinar, we inspect this last application of induction hardening since it is one of the main industrial applications for surface material treatment. Some mechanical parts which are frequently exposed to continual external stresses require hardening processing to provide optimal performance and long expectancy life. So induction hardening allows an efficient way to thermally treat gears, shafts, bearing tubes, pipes, etc. So induction is the perfect solution for many hardening requirements, like the fast heating rate, the uniform temperature, and the easy heating control. This process of hardening is widely used to surface harden components based on induction heating, whereby the conductive materials are rapidly heated and quenched to induce martensity transformation and then increase the surface durability and the residual stresses of the component. Unlike processes where heat is generated by an oven or a flame, the heat in induction hardening is created directly in the component. The hardening process can be precisely controlled by many factors, which will be mentioned during the next slides. There are many types of induction hardening, but they could basically even static or progressive, where we have a moving or a rotating parts like the inductor or the heated part. This process is characterized by a fast heating rate with a short cycle time. It can be applied to external as well as internal surfaces, and it allows a well-selected localized surface hardening by creating higher residual local stresses without affecting the rest of the parts. It helps to get an easy controlled heating where the heated parts have a higher fatigue strength without any limitation of hardening profile or workpiece geometry. Now, as an engineer or designer, before going to the experimental heating steps, several factors can be involved in the design, modeling, and simulation steps of induction heating. Those factors affect strongly the desired final results, like the achieved temperature, the heat profile, the hardening rate, and even the material state. And those factors could be related to the cut design, like the inductor design or the inductor position according to the heated part, or could be directly related to the main process parameters, like the heating time, the used frequency and skin penetration depth, the used heat material, the excitation power supply, the speed of the rotating part for progressive hardening, or to the generated electromagnetic and thermal stresses. All of those factors could be covered using EMS for SolidWorks. But for our today's webinar, we are going to focus on the highlighted aspects, in which SolidWorks multi-configurations features is used to vary the inductor design, as it is the most important factor that defines the heating profile and distribution. The heat transfer analysis will be performed using transient thermal solver to model the time-varying heating operation of the spear gear. Later on, to optimize your hardening process in terms of optimal frequency and hardened penetration depth, a parametric analysis coupled with thermal for inside EMS will be used to reduce the simulation time and compare the effect of those factors on your design within the same study. The accuracy of the computed temperature could be also improved with the use of temperature-dependent materials to converge to the realistic working condition of the hardening process. And finally, heat and mechanical stresses could be studied to estimate the mechanical deformation caused by thermal stresses and generated forces inside both the coil and the hardening component. Now, before moving to the simulation results, let's go through a quick exploration of EMS interface inside SOLIDWORKS and check our main features that will be used for today. And here we are, as you can see in front of you, we have here the SOLIDWORKS interface with this studied example of induction hardening, which is made from this coil part and the component to be heated, which is a sphere gear. Now EMS is fully integrated inside SOLIDWORKS. It is an add-ins inside it. As we can see here from this add-ins window for SOLIDWORKS, EMS could be added with a simple click. So once it is checked, it shares with SOLIDWORKS many great features which allow the user to work on both the CAD design and also the electromagnetic simulation with the multiphysics analysis inside the same interface. Once it is checked, an EMS tab manager is added, from which the user can define his own study. EMS has 6 different study types, 3 for the magnetic modules and 3 for the electric modules. For the magnetic analysis, we have the magnetostatic, we have the AC magnetic for frequency domain, and the transient magnetic for time domain. And for the electric studies, we have the electrostatic module, the DC conduction, and finally the AC electric. As you can see, there are many other options which are available for each study types, like here the parameterization, which is available for many study types. Now let's move to the multiphysics analysis. From this second coupling analysis, 4 types of multiphysics coupling could be used. For the heat transfer analysis, we have the thermal coupling with its both types, steady state and also transient for time varying heat transfer. For the mechanical deformation, we have the structural solver, which allows to compute mechanical deformation stresses and strains. This type of coupling could be also coupled to the thermal for the case of thermal stresses, where the thermal solver will compute the temperature of the whole component and then will feed it to the structural solver to compute the corresponding thermal stresses. We have also the motion coupling analysis for the moving and rotational parts using the motion study of SOLIDWORKS. And finally, we have the coupling to circuit. Now, since we will work on the coil design selection, we already talked about SOLIDWORKS multi-configuration, which is available from this tab. This feature will allow us to study many coil designs inside the same project. As you can see here, with a simple click we can switch from a configuration to another, and the corresponding electromagnetic study will be activated synchronously. And here the third coil design. Now, when creating a new study, an EMS tree will be added, as you can see from this already defined studies. For this first study that we will use in our simulation, it is an AC magnetic study with thermal coupling. As you can see in front of you, many sections, starting from the materials in the top to the results in the bottom. For the materials, if you want to apply a material, assign a material to one or more component, you have to just select and right click apply materials. A well classified and rich material library will be shown in the right side. As you can see, it is a very rich material library with different categories, from which the user also can customize his own material by adding a new library or a new material. Under this section, it comes the electromagnetic and thermal inputs from which the user can define his coil setting, excitation, forces, and also thermal boundary condition in this case. Then we can find this mesh folder for mesh setting. It is equipped with flexible and advanced mesh tools and techniques, which allows the user to specify his own mesh control by defining his mesh size in a specific surface or bodies. And finally, after solving your study, two sections of results will be added. For the electromagnetic folder, we have here the electromagnetic results and the thermal results. And if structure is also added, another section of our structural results will be added in the bottom. So EMS has several post-processing options which make the results exploring much easier and efficient. Now let's move to the simulation part. AC module from EMS is used for a frequency domain. As already mentioned, the heating component is a sphere gear design with 9 teeth and module equal to 4 mm. The required hardness and cost are very important factors to consider when selecting materials for the hardening gears. The used material for our simulation is stainless steel SUS 304. Generally, during hardening process and before being quenched, steel is heated to a temperature slightly higher than the upper critical temperature, which would be between 750 and 950 degrees Celsius, which is defined by the red line according to the scale phase diagram in this figure. This condition defines the desired temperature that we will try to reach during our simulations. Now what about frequency? According to the required hardening depth, frequency is selected, which means to accomplish a hardening depth of 1 mm or less, higher frequency between 200 and 900 kHz should be used, and for the 2 mm depth and greater, medium frequency between 10 kHz and 50 kHz is required. For our case, and according to the module of the used gear, the optimal heating frequency could be around 22 kHz and 37.5 kHz. When hardening is performed, uniform heating is required for the hardening penetration depth. So trying to select the optimal coil design to get a good heating profile is very important. SOLIDWORKS multi-configuration features coupled with EMS simulation is then the perfect solution for it. As we already mentioned during the live demonstration, 3 different coil designs were performed to analyze the heating profile of the studied gear during this process. Now let's check together how will be the temperature distribution for each design. For this first coil design, which is made of a one-turn inductor with the gap separating the entry and exit ports, if we consider static hardening, when both the inductor and the gear are fixed, a 5 seconds of heating for a frequency of 30 kHz are enough to heat up the gear to the desired temperature mentioned in the previous slide. So as a result of it, we obtain the following induced eddy current density distribution, which looks uniform and acceptable, where the maximum is concentrated in the root regions between the root region of each teeth. But what about the temperature? As you can see from the following temperature distribution, heat is not symmetrically distributed, essentially around the teeth region, even if desirable temperature rates are attained. So after being quenched, hardening won't be uniform too. Then this is not good enough. Now, if we try to use a closed coil design, because now we know that the problem is in the gap there between the entry and exit ports. Let's see if the heat profile will be adjusted or not with this design. We will consider the same heating and excitation conditions as the first one. Our current now looks much more symmetric. The same thing for the temperature. So it follows the current profile and achieves the required heating rates with an averaging of 800 degrees Celsius for the desired depth. So this design solved the symmetry issue even if the maximum where the red zones doesn't cover all the teeth contour, but it will be improved later when playing with the material properties. Now, what about the high excitation current? Could we solve this with another coil design? Let's see with the third inductor geometry. Now we have a multi-turns coil for the same heating time and with the same frequency. With this design, we could use only the half of the excitation current to achieve the same current and temperature as the previous designs. The current results looks acceptable and symmetric, but for the temperature is not the case. As you can see, a big difference in temperature values between the teeth and the uniform heat profile is lost with this design, even if we profit from a lower excitation currents. So, for our static hardening, it will be better to use the second closed coil design for the rest of our investigation. And now, let's see how the variation of the frequency could help to select the optimal one that improves the heating profile and rates. So, a parametric analysis coupled with thermal is performed to select the optimal frequency and its impact on the skin depth and eddy losses. Now we are interested with the supply frequency, which will vary between two values, a minimum of 25 kHz and a maximum of 100 kHz. And automatically it affects the skin depth according to the skin depth expression. So when the frequency gets higher, more fine mesh elements across the skin depths are needed, which could be easily controlled by mesh refinement parameterization for the skin depth variable, as it is an automated process in EMS. So as a result of this frequency sweep, we have in the left figures the variation versus frequency of skin depths as well as the attained eddy losses, which increase proportionally to it. The right plots show the loss density distribution for the first and the final frequency for 25 and 100 kHz, from which we can easily note the localized losses within the desirable penetration depths. Now, if you want to have a close idea about precise numbers of the loss densities, then you can use the 2D plot of the spatial variation between 2 points A and B inside one particular tooth, which were selected from the gear base circle, and with plotted versus frequency. So we have now in the right figure the interpolation along the AB line for the different scenarios. We have a symmetric distribution from which we can easily notice the variation of skin depth via the increase of losses density at the right and left regions, which define the hardened tooth contour. Now, what about temperature results? Let's have a look on it since it will define the hardening rate. For the following temperature results, at the first and the final used frequency, we can conclude that lower frequencies are used to heat the gear root region, and higher frequencies are essentially used to heat the top teeth surfaces and at higher temperature values, which is essentially used for the dual frequency hardening type. So, we saw the impact of frequency sweep on the losses and skin depths, how to select now the optimal frequency according to temperature. If you remember from the steel phase diagram that we showed from the previous slides, steel should be heated to a temperature between 750 and 950 degrees Celsius. So for our case, and based on the second plot of the variation of temperature versus frequency, we can confirm that for our heated gear design, frequency should be around 30 kHz. Now let's move to the effect of material property. How could it improve the heating profile? So, to get as close as possible to the concrete hardening conditions and to accurately predict the achieved temperature magnitude and profile, EMS allows to use nonlinear temperature depending material properties for electromagnetic, thermal and mechanical properties, with an internal two-way solving between the electromagnetic and thermal solver within the same analysis and inside the same interface. For our case, we use a temperature-depending thermal conductivity of the heated gear, and we found that the heating profile of the heated gear is more accurate and realistic, as you can see from the second figure, compared to the case of constant thermal conductivity. Now we got a well uniform heating profile. From the same obtained temperature distribution, we selected 3 points, T1, T2 and T3, from which are located respectively at the inner diameter of the gear hole, at the gear root and at the top tooth surface. The right plots are showing the temperature variation between T1 and T2 and between T1 and T3. For the space between T1 and T2 and T3, which defines the working depth, the variation of temperature is very small, between 820 degrees Celsius and 870 degrees Celsius. So it is well defining the required temperature rates for the hardened profile. Now what about the generated electromagnetic and thermal stresses? High current may result in higher thermal stresses and Lorentz forces in both gear and inductor parts, which lead to structural deformation. EMS can be used to analyze this behavior. In addition to temperature, EMS computes Lorentz force in conductors with currents, and both of them, I mean the thermal response and the electromagnetic, including the Lorentz and magnetic forces. So for the coil side, high circulating current generates Lorentz force, which could be computed and visualized by force distribution in the first figure in the left. When it is fixed from the top and the bottom faces, the coil is deformed under the effect of those forces. So EMS allows to compute and visualize the deformation, which is symmetrically distributed across the coil and achieves a maximum value of 7 nanometer. Same thing for the heated gear. The force density distribution is shown by the left figure. Maximum forces are following the eddy currents profile, which are concentrated at the gear root regions. Now when fixed from the central hole, maximum gear deflections are localized across the teeth parts. Overall, under only the effect of electromagnetic forces, the attained stresses are relatively tolerable and acceptable. Now, when added to the electromagnetic effect, thermal stresses allow to obtain the following results. So, after solving the thermal part, thermal loads, which are temperatures, are fed to the structural solver to compute the thermal stresses sequentially and then predict the produced mechanical deformation. The attained displacement is significant compared to the electromagnetic effect alone, which confirms the strong effect of temperature on the gear structure after being extremely heated. Now we conclude with those results. To summarize, EMS for SOLIDWORKS covers the different design issues posed by the single-shot induction hardening process in static case. Through this webinar, we tried to show you how EMS allowed to select the optimal coil design for static induction hardening and to select the optimal frequency according to the desired penetration depth. Also, the effect of nonlinear temperature-dependent material properties on the heated profile was investigated. And finally, we tried to estimate the generated deformation of the coil and gear under electromagnetic and thermal stresses. Thank you for your attention and time, and I hand over the screen again to my colleague Carl.
Thank you, Asma. We used EMS product to simulate an induction hardening problem. Let us take a quick overview on EMS software. EMS product offers electrical and magnetic solvers. In addition, few multiphysics options are available with this product, like thermal, motion, linear statics, and circuits. EMS software is available in 4 package options, namely electric, magnetic, professional, and premium. To get more information on the software packaging and pricing, you can connect with me after this webinar. To simulate an induction hardening problem using EMS software, magnetic package with thermal and linear statics add-ons should be used. Now this slide represents a small subset of capabilities available in our EMS software product. To simulate an induction heating problem, 3 capabilities are highlighted and utilized in the product demo you saw earlier. Number 1, multi-configuration support. This capability of SOLIDWORKS enables users to maintain multiple versions of a part or an assembly in a single file. The differences between configurations are established by changing dimension values, suppressing features, and changing other parameters. Number 2, thermal analysis. Through this multiphysics add-on, you can calculate temperature distribution, temperature gradient, and heat flux in your model. Number 3, AC harmonic and transient magnetic solvers. These solvers can help a user to analyze magnetic fields, forces, eddy currents, losses due to time harmonic and time varying currents. Now let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into 2 categories: applications related to low frequency simulation and applications related to high frequency simulation. Within low frequency category, we offer 3 products: EMS 3D, EMWorks 2D, and Motor Wizard. These products can be used to design and simulate applications like cables, insulators, bus bars, solenoids, magnet arrays, eddy current braking systems, wireless charging, induction heating, transformers, electrical machines, etc. And within high frequency category, we offer one product known as HFWorks. This product can be used to design and simulate high frequency applications like antennas, waveguides, filters, resonators, connectors, etc. With regards to learning resources, we offer various free learning tools. With the software purchase or an evaluation license, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. Anyone interested to get more information on our products, including trial, quotation, can go to our Contact Us page on EMWorks website. You can select the appropriate category and submit your request, and one of our representatives will reach out to you soon. Before we answer your questions, I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you again.